In the next few slides, we're going to discuss some of the properties that make enzymes attractive catalysts. And I mean attractive catalysts in the sense that they can be used for many different applications. They can be used in washing powder, they can be used for the synthesis of pharmaceutical building blocks, and many other applications. So you might ask the question, what is the difference between an enzyme and a normal chemical catalyst? And you see that a normal chemical catalyst usually tends to be rather small, whereas enzymes are up to 50 times heavier than normal chemical catalysts. So you might also ask the questions, why does nature invest so much into the synthesis, into the buildup of such huge structures, while seemingly a small chemical catalyst can do the job as well? Well, the answer to this is, it is the three-dimensional structure. It is the very well-defined three-dimensional structure of an enzyme that in the end builds up the enzyme active site and brings up the reagents and the substrates together to form the catalytic active site and make the reaction happen. So there are many factors that actually influence or are influenced by the structure of the enzyme for the catalytic properties. So one of them is aligning the reagents. Another one is the stabilization of high energy intermediates in the reaction. And of course, there's many other factors which, honestly speaking, we today do not understand fully. So there is still a lot of research necessary to understand how enzymes, for example, dynamically participate in the catalytic process. So for today, I want to focus only on the first two topics, on the alignment of the reagents and on the strategies to stabilize reactive intermediates. And to give you an idea how important bringing reagents together is, I mentioned this very simple chemical reaction. So you see an ester, which is hydrolyzed into the carboxylic acid and the alcohol. And for example, you can use acetate or any other catalyst to accelerate this reaction. So what a colleague of mine actually did, he was comparing the rates of this very simple chemical reaction by putting the catalyst, the acetate, shown in green here, into the reaction mixture, putting the rate of this reaction to 1. And then what they did was they actually built in the catalyst covalently into the molecule itself. So they were basically eliminating the diffusion limitation for the catalysis reaction. So the catalyst, also shown in green below, is very, very close to the reactive site and can catalyze the reaction. And what you see is that simply by covalently linking the catalyst to the molecule, you get a rate acceleration of approximately 1 millionfold. So bringing the catalyst with the reagents in close vicinity is very important to eliminate diffusion limitations. And enzymes actually do this as well. And I want to discuss with you the example of the so-called serine hydrolases, simply because these enzymes have been investigated in great details already some decades ago. So what these enzymes do is they basically catalyze the same reaction that we have discussed before. They hydrolyze esters into acids and alcohols. But how do these enzymes do this reaction? Well, the strategy is they use a so-called catalytic serine that you see up here. This is basically an alcohol, and this alcohol attacks the carboxylate group and throws out the alcohol group and makes a new ester between the acid group and the enzyme. So this is the catalytic strategy. Unfortunately, serine itself is not very nucleophilic. So the tendency of serine to nucleophilically attack at the carbonyl group is practically 0. So in order to increase the activity of the serine, the enzymes use the so-called catalytic triad. And this is what you see here. So next to the serine, there is a histidine, which basically acts as a base. So it abstracts a proton from the serine. In a way, it generates a negatively charged serine, which then very nucleophilically can attack. The problem then there would be that the histidine taking up another proton would get a positive charge, and this positive charge would be energetically rather unfavorable. That's why we have the third amino acid, the aspartate, which takes up the proton from the histidine and thereby prevents the buildup of a positive charge. So with this, we cleave the original acid, the original ester moiety. We get the internal covalent ester with the enzyme. And in order to complete the reaction, basically, we just need to reprotonate it. So in order for example, water to attack, so here we want water to attack this covalent ester with the enzyme, we need to turn the serine into a good leaving group, which is not a good leaving group, but once we protonate it, it becomes a very good leaving group. And luckily, we can get a proton from the histidine, which donates a proton to the serine, makes it a good leaving group. And in order to prevent the buildup of a negative charge at the histidine, which again would be energetically very unfavorable, we just take the proton from the aspartate and donate it back, so we have completed the reaction. So all these three amino acids are important for the catalytic reaction to cleave the ester into an acid and an alcohol. And it's also very important that these three amino acids, the serine, the histidine, and the aspartate, are very close to each other. And this is what you see here in a three-dimensional structure of one of these serine hydrolases. So here you see the serine, to the left you see the histidine, and to the far left on the bottom you see the aspartate. So you see that all these three amino acids are fixed in the spatial orientation to each other in such a way that the proton transfer can occur ideally. And this can only happen because the amino acids are in a very well-defined enzyme active site. And this is why we actually need this very complicated, this very huge structure of an enzyme to build the framework for the enzyme active site for the reaction. If you would try to do this reaction in solution and just add histidine, serine, and aspartate, the likeliness that all these three amino acids together with the substrate would meet at one point in time in one position in the right orientation to each other, this likeliness is practically zero. That's why if you put in all these amino acids into a solution, nothing would happen. But if you put an enzyme where these three amino acids are located in one defined position to each other, the reaction is very efficient and you have enormous rate accelerations. So this is the mechanism of the catalytic triad. I shortly want to discuss with you another catalytic mechanism, and that is the so-called oxyanion hole. So what you see here is a typical energy diagram for catalysis. So we have the starting materials at a certain energy level, we have the products at a lower energy level, and in between we have the so-called transition state, which is usually very high in energy. And you see the transition state in this reaction, we have a negatively charged oxygen anion, which is, and we have transformed the tetrahedral, we have transformed the planar ground state into a tetrahedral intermediate. So the substituents also get closer to each other. So we have the steric repulsion, we have the localization of one negative charge. So that makes the intermediate very high in energy. And you can imagine yourself climbing a mountain takes time, it's very slow. So if you have a huge mountain to climb, the reaction will be rather slow. So if we find a way to reduce the energy of this intermediate, then we can reduce the height of the mountain and we transform it basically into a hill. And climbing a hill is much easier than climbing a mountain. So you can imagine that this reaction will be much faster. And that is what the serine hydrolyzers actually do. They provide a so-called oxygen anion hole. This you can see here in yellow. This is a region within the enzyme, again, very well localized, which contains a lot of positive charges, which contains hydrogen donors, which can interact with a negatively charged oxygen anion and thereby stabilize this oxygen anion. So you see that compared to the reaction without catalyst, without the oxygen anion hole, the reaction with the oxygen anion hole is much faster because the energy of the intermediates is much lower. So these are some of the features of catalysis. I've just mentioned the serine hydrolases. You can be sure that for many other enzymes, many different strategies exist, but time is not sufficient to go through all these strategies. So there are reasons why enzymes have this very complicated, huge structure that is built up of the enzyme active site that makes them attractive catalysts for chemical reactions ranging from washing powder to the synthesis of pharmaceuticals. But of course, we all know that enzymes have been evolved to sustain the survival of the organism. They have not been evolved to perform chemical reactions as we like to have them. So there is a very high likeliness that a given enzyme that you isolate from a bacterium, that you isolate from soil, that you isolate from something else, does not really meet the requirements of the chemical reaction, either because it's not stable enough, either because it's not fast enough, or the selectivity of the natural enzyme is not high enough. And that's why we have invented directed evolution, in order to improve the properties of an enzyme to the desired properties that we want to have from them. And this is going to be discussed in the next few slides.